We now want to move on and we want to talk about if we take a permutation and we write it as a product of transpositions, is this unique in any way? If you toy around with this a little bit, you'll see pretty quickly that there are lots of different ways to take an arbitrary permutation and write it as a product of transpositions. So it is not true that there is a unique way to write a permutation as a product of transpositions in general. However, there is something that is unique about writing a permutation as a product of transpositions, and what's unique about this is the parity. So if I can take a permutation, suppose I take a permutation f in Sn, and n is greater than or equal to 2, then what we can prove is that if we can write f one way as a product of transpositions, and the number of transpositions that show up is an even number, then no matter how you write f as a product of transpositions, it will always be written as a product of an even number of transpositions. And similarly, if you took f and you wrote it as a product of an odd number of transpositions, then every decomposition of f that you could possibly come up with as a product of transpositions will always require an odd number of transpositions. So again, it's not that the decomposition of f as a product of transpositions is unique, it's that the product of f is the parity of that decomposition is unique. It will always be an even number, it will always be an odd number of transpositions. Now, this is a big theorem, a good theorem, and an important theorem. However, we're not going to do the proof of this theorem in this set of slides. What we're going to do is we're going to talk about the general outline of the proof, how you go about proving this. We're going to work an example to kind of give an idea for the flavor of the proof, and then we're going to prove sort of a corollary of this theorem. So the key to proving this theorem is in a very technical lemma, which shows that the identity of S sub n can always be written as an even transposition. So, and the way that that lemma is proven is you take the identity. We've already discussed in a way how to write the identity as a product of transpositions. The identity is just a huge collection of fixed points. So if you follow the algorithm in our previous video, you can take the identity in Sn, where n is greater than or equal to 2, and you could always write the identity as just 1, 2, 2, 1, which is a product of two transpositions. And then the way that the proof goes, it says, suppose that you had this arbitrary representation of the identity as a product of some number of transpositions, and you could think about it as being as complicated as you'd like. And what you're going to do is an inductive argument. You're going to try to take this arbitrary representation, which could be messy and crazy and ridiculous, and you're going to try and rewrite that arbitrary representation in a way that involves fewer transpositions. And what you're going to want to argue is that you sort of take an arbitrary representation and you get rid of an even number of transpositions that appear there, and then you'll have a smaller representation. You can use an inductive argument to then say, well, that smaller representation has an even number of transpositions, and I took away an even number of transpositions, so altogether my original representation must have been even. So that's the outline of the proof of this very technical lemma. What I'd like to do in the next slide here is just give an example of the technique that's used to take this arbitrary, potentially messy representation of a permutation and to rewrite it. So to really give you the tools for taking a big long permutation, big long product of transpositions, and rewriting it in an easier way. So here's our example. Let's suppose that f is some sort of permutation, don't really know what it is, but it's written this way as a product of transpositions. 1 goes to 3, 1 goes to 4, 1 goes to 2, then 3 goes to 1, 3 goes to 2, and 3 goes to 4. Now, if we really wanted to, and maybe it's a good exercise if you're new to working with permutations and combining them, you might want to go through and see if you can figure out what the function f is right away. I'm not particularly interested with that right now. What I am interested in is saying, how could I take this sort of long, seemingly random product of transpositions and rewrite it in a more condensed form? How can I simplify what I've been given here without actually just chasing through all of the transpositions? Now, what I want to do here is a transposition is equal to its own inverse, and if I look through this particular permutation that I've been given, I do see that here 1, 3 is this first transposition I have. I have another 1, 3 sitting over here. And if I could get those two permutations next to each other, then they're inverses of one another and they could kind of cancel away, and I could take this long messy permutation that I have and I could make it smaller. However, the problem is that always remember that permutation groups are non-abelian groups, and so just because I see an element right here and its inverse over here does not mean that they cancel away. If I want them to cancel away, I need them to be next to each other, and I'm not simply at liberty to just start moving things around, right? This is a non-abelian group. In general, 1, 3, 1, 4 is definitely not equal to 1, 4, 1, 3. The permutation 1, 3, 1, 4 sends 1 to 3, it sends 3 to 4, and it sends 4 back to 1. This permutation over here does not do that, and I'll leave it to you to check. However, it is still possible to take the 1, 3 and sort of put it on the other side of not of 1, 4, but of some other transposition. So if I want to take this 1, 3 and sort of move it across the 1, 4, it's not true that 1, 3, 1, 4 is equal to 1, 4, 1, 3, but it is true that 1, 3, 1, 4 is equal to 3, 4, 1, 3. And you can check that by just sort of checking that 3, 4, 1, 3 also sends 1 to 3, 3 to 4, and 4 back to 1. How this is used for us is we take f, which I've simply rewritten here over on the left-hand side of this equality, and where I have this 1, 3, 1, 4, I've simply moved the 1, 3 over one spot a little bit closer to this 3, 1 here, and I've replaced this 1, 4 with the 3, 4 over here in order to make sure that I'm still mapping everything to the right place. So that's what I've done initially, is I've taken this 1, 3 and I've sort of scooched it one place over to the right, a little bit closer to its inverse here, which is 3, 1. Now, I'm still not, after having done this trick once, I'm no better off than I was before. Nothing here cancels. I don't have any inverses next to one another, and this is a non-abelian group. So I've got to keep moving this 1, 3 all along this permutation until it meets up with this inverse, and at that point I'll be able to cancel these things away. So the next step that I need to do is I need to take this 1, 3, 1, 2, and I want to see if I can take this 1, 3 transposition and move it to the other side of the 1, 2. So again, I'm not at liberty to just rewrite 1, 3, 1, 2 as 1, 2, 1, 3. Those are not the same thing, but I can, if my ultimate goal is just to move the 1, 3 to the other side, I can replace 1, 3, 1, 2 by 2, 3, 1, 3. That does happen to be the same permutation as 1, 3, 1, 2. And it has the effect that we want, where it takes the 1, 3 and it moves it over to the right a little bit more. So I can take my original permutation f, which by this equality up here is equal to 3, 4, 1, 3, 1, 2, 3, 1, 3, 2, 3, 4. And I can now replace that 1, 3, 1, 2 from up here with 2, 3, 1, 3, which the ultimate goal was to put the 1, 3 right here next to its inverse with 3, 1 right here. And once I've done that, I can replace these two permutations with just the identity and kind of delete that from here. So I can rewrite f, which had 1, 2, 3, 4, 5, 6 transpositions here. I can take f and I can replace it with something that only involves 4 transpositions. Now certainly we agree that something with only 4 permutations is going to be a lot easier to think through than something that has 6 permutations. And so we've taken this original arbitrary permutation representation, we've made it simpler by getting rid of some of the permutations that we see there. Makes it a little bit easier to think about. In fact, at this point, we can give away the game. Now we've got a 2, 3 sitting right here next to a 3, 2. Those two transpositions are the same and they're inverses of one another. And so the 2, 3 and the 3, 2 actually should cancel away. And once they're gone, the 3, 4 and the 3, 4 will be next to each other. Those are inverses. They will also be replaced with the identity. And so altogether, I said it was a good exercise to work out, but we've actually worked it out in doing this example. This permutation F is actually the identity. So here's one strange way to think about the identity. Don't know why you'd want to think about it that way, but if you did, you can prove that it is the same as ascending 1 to 1, 2 to 2, 3 to 3, and 4 to 4. So what we've done here is we've taken a representation F, we've replaced it with an equivalent representation, and it has 2 fewer transpositions, and that really is a key point. You take something that originally had 6 transpositions, and because you're taking one of those transpositions and canceling it with an inverse, you're always deleting 2 transpositions at a time. And so if I go down from if I started out with an even number of transpositions, and at each step of this simplification process, I'm taking the same number of permutations, I'm taking 2 transpositions and replacing it with 2 transpositions. That's not changing how many transpositions there are when I rewrite. At this stage of the game, when I have a transposition next to its inverse, I am changing the number of transpositions there are, but I'm taking them away in even numbers. So I had an even number, start taking away even numbers of them, and I'm always going to end up with something that has an even number of transpositions. So that's really, you formalize things, everything gets letters instead of numbers, and you do a very nice formal inductive argument, but that really is the idea behind this proof of taking the identity and showing that it's always can be written as an even number of transpositions. Once you prove that lemma, and you prove that the parity, this always even, always odd theorem, right, what we can do is we see that every time you have a permutation and it's written as a product of transpositions, the parity of such a decomposition is unique. Then we can prove this very nice lemma, which is helpful to us and which is really the point and the reason that we care about if a permutation is an odd permutation, meaning that it can be written as an odd number of transpositions, or if a permutation is an even permutation, which means that it can be written as an even number of transpositions. We have the following lemma, which is that if we look at the set of even permutations inside Sn, which we denote by A sub n, then this forms a subgroup of Sn. And the terminology when you're talking about this particular subgroup, A sub n, is to call this the alternating group. So Sn is the symmetric group and A sub n is the alternating group. And that is the subset of Sn of all of the even permutations. Now, the last thing that I would really like to do before we get to our summary in this set of slides is to prove that A sub n forms a subgroup, which is a very standard two-step subgroup test. So either using that lemma that we didn't formally prove or just doing this explicitly, we notice that the identity function belongs to A sub n. It's an even permutation because you can take the identity and you can write it as 1, 2, 2, 1. So that contains 2 transpositions. The identity is an even permutation. And this accomplishes the first criteria that we need, which is that A sub n is a non-empty subset. The next thing that we need to do is show that A sub n is a closed subset, which means let's start out by taking 2 elements, let's call them f and g, that belong to A sub n. And what we want to do is we want to show that when we take their product inside Sn, that it also belongs to A sub n. Now, because f and g belong to A sub n, they're even permutations. Again, what this means is that if we take f, it can be written, and we write it as a product of transpositions, which we know we can do, then it can be written as 2k transpositions, an even number of transpositions, and similarly, g can be written as 2l transpositions, where k and l are positive integers. Now, if we go ahead and we look at f combined with g, let's not even figure out what that is and try to simplify it and rewrite it in disjoint cycle notation. Let's just take f, let's write it as the product of 2k transpositions, like we know we can do. Then let's take g, let's write it as the product of 2l transpositions, which we know we can do. And the result will be the same as taking f and combining it with g. And f and F combined with G, we have found one particular representation of that as a product of transpositions. In particular, it's 2k plus 2l transpositions, which is 2 times the quantity k plus l transpositions. That is, it's an even number of transpositions, the 2k that we need for F, an even number of transpositions, the 2l we need for G, and altogether we have 2k plus 2l transpositions there. And this exhibits that A sub n is closed. Last but not least, we need to show that A sub n is closed under taking inverses. So again, let's start out by taking F, an element of A sub n. So what this means is that F can be written as A1, A2, all the way up through A sub 2k, where each one of these A sub i's is a transposition. So write it as, 1, 3, 1, 4, whatever. If we take a look at F inverse, we just use this sock-shoes property, kind of generalized out to 2k things, then the inverse of A1, A2, all the way out through A sub 2k is going to be A sub 2k inverse, A sub 2k minus 1 inverse, and so on and so forth, all the way down through A sub 2 inverse, A sub 1 inverse. And the nice thing is that transpositions are their own inverses, and each one of these A sub i's is a transposition. So if we want to look at A sub 2k inverse is really just a fancy way of saying A sub 2k. A sub 2 inverse is really just a fancy way of saying A sub 2, and so on. So here is one way of writing F inverse as the product of transpositions, A sub 2k, A sub 2k minus 1, all the way on down through A sub 2, A sub 1. And what we've shown is that F inverse can be written as 2k transpositions, as a product of 2k transpositions. And this is enough to show that A sub n is closed under taking inverses. Now, in summary, after studying these slides and looking over your textbook, there are a few things you should be able to do. The first is you should understand the 3 main ways that we represent elements of Sn, and you should understand the relative strengths and potentially weaknesses of each one of these representations. So the ones I'm talking about are tabular form to represent a permutation, disjoint cycle notation for representing a permutation, and writing a permutation as a product of transpositions. You should also be able to do this yourself. So if you're given an arbitrary member of S sub n, you should be able to represent that permutation in any one of these 3 ways, either as a table in disjoint cycle notation or as a product of transpositions. And last, you should understand the statement of the always even, always odd theorem and the definition of the alternating group. We haven't really discussed in this series of videos the strength and the necessity of understanding the alternating group, but this is something that is going to come up for us a lot later on in the course, so for now we'll just have to leave it as a bit of foreshadowing. It may still seem a little bit mysterious, but alternating groups are in fact a very important collection of groups, and we'll see that more later on.